Good afternoon, everybody, and welcome to this week's Geo Lecture. This afternoon, we have got Dr. Laura Gregory with us. She's an earth scientist at the University of Leeds and specialises in active tectonics and earthquakes. And to do so, she uses geochemistry and fieldwork investigation to study activity in tectonics over a range of timescales. So this should be a very interesting presentation. So when you're ready, Laura.
Great, thank you. Okay, thank you very much, Isabel, for that nice introduction. And thank all of you guys for coming along to this talk. Hopefully you enjoy it. So I am an earthquake geologist, and so I look at earthquakes from a kind of surface point of view. So I also do a bit of geography. And what I'm going to talk to you about today is how we can use kind of tools in the landscape to understand how earthquakes might affect the populations that are living near them and are susceptible to earthquakes. So here you can see in this image a photo from Italy. And this photo was taken after an earthquake in 2016 that affected the area quite strongly. And you can see all these cracks in the ground. And so those cracks are representing what happens at the Earth's surface after an earthquake. My colleagues and I happened to actually be in the area for this earthquake. And so we experienced firsthand how scary the earthquakes can be and how much it affects the local populations. And so what we're going to do today is kind of go over exactly what an earthquake is and what we know about earthquakes as scientists who are studying them. Then we'll talk about kind of how we can use different tools from looking at the landscape and from lots of other aspects of earth science research and geographical research to better understand how earthquakes might affect populations living nearby to fault lines. And so we'll talk about how to make a hazard map, basically. And then we will talk a little bit about kind of how societies may deal with earthquakes and what impact that earthquakes have on society. So a lot of this is on the kind of physical geography side of geography, but we'll also talk somewhat on how this impacts society as well. So hopefully you'll find it interesting, and hopefully you'll learn something about earthquakes that you didn't know before, and kind of how we as earth scientists and geographers can use lots of different tools to better deal with this hazard that earthquakes present. Okay, so when we think about earthquakes, actually, they're pretty rubbish. And so I'm a scientist who studies earthquakes, and I understand that they are rubbish. They cause lots and lots of devastation. So here you see a few examples of damage after major earthquakes that you might have heard of in the past. They cause damage that's really difficult to recover from. So it can be quite hard to restore a building that has partially collapsed or recover when your whole entire village has been destroyed. They cause a lot of financial damage and, unfortunately, human casualties as well. And when we think about earthquakes, it's a good idea to actually be afraid of them as a society and not petrified in fear. So we don't want to be so scared that we don't do anything about it, but we want to be calmly afraid and have an approach that we actually can take some mitigating kind of actions to deal with the hazard that is presented by earthquakes. And that was kind of stated by the Japanese Prime Minister. Japan has a lot of earthquakes, and he said we should be calmly and appropriately afraid. And I think that's completely true when we start thinking about earthquakes. But us as scientists can really contribute to this problem, because we can start to understand the kind of fundamentals of why earthquakes happen and where they might happen. Now, when you first start thinking about earthquakes, a lot of people, the very first question they ask me is, can we predict earthquakes? And the answer is no. We definitely cannot predict an earthquake. So anytime that you've heard someone say that they can predict an earthquake or that we might be on the verge of predicting earthquakes, currently we cannot do that. And we probably won't be able to do that in our lifetime because there's a lot that we still don't understand about them. And so that prediction is often related to like animals reacting funny before an earthquake happens, or radon gas being measured, things that sound a bit crazy and are really actually difficult to prove. And so right now there's no kind of known phenomena that we know that tells us an earthquake is coming. But there is a lot that we can do to build up a forecast of earthquakes. And so that word forecast is the appropriate term to use when we're talking about whether we can know when an earthquake or where approximately an earthquake is going to happen. And so here we have our hurricane forecast. Now, when we're dealing with hurricanes, so I'm actually from Florida, I'm from right in here. So I understand what it's like to deal with a hurricane coming. There's loads of data, we can literally see it coming, there's a bit of warning, and we can kind of prepare for the hurricane to arrive and batten down the hatches and even escape if we need to. But with earthquakes, it's a little bit different. So we don't have the kind of immediate change in information leading up to an earthquake, but we can produce kind of a longer term forecast of where earthquakes may happen and when using geological information. And so we kind of approach it in the same way that we would a hurricane forecast, but we look at what's going on all the time and how likely an earthquake is to happen. And just like how I used to prepare for hurricanes by making sure we had supplies in the house, we can do the same for earthquakes. So there's lots of things that you can prepare if you live in a place that has earthquakes to get ready for one to happen. And we really encourage people to do so and to kind of always be ready. But what we want to do is get better at doing these forecasts as earth scientists. And so there's a few things that we need to take into consideration. So I'm going to tell you about what we know about faults and how we can start to incorporate information into these forecasts. So if we look at this map, we can see, I hope you can recognize the Earth's tectonic plates. And so those are in different colors on this map. Those are all the big plates on the Earth's surface that are jostling around. And you can also see lots of black dots on here. All of those black dots are earthquakes that have happened over the past 100 years. And there's also these really big earthquakes that have happened outlined in white. So those are major earthquakes that have happened in the past. So the first thing we want to know is, where are the earthquakes going to happen? If we're living here in the UK, which is barely even on this map, it's in the middle of a plate, we don't really get that many earthquakes. But if you're living somewhere like California or Japan, we might get lots of earthquakes. And the reason is that, as you can hopefully notice, a lot of earthquakes happen at the boundaries of the plates. And so at these boundaries, the tectonic plates are interacting with one another. They're either colliding and subducting, they're sliding past, or they're pulling apart. And at these boundaries, there's definitely going to be a lot of earthquakes. So that's our first order observation. Where do earthquakes happen? They happen associated with the boundaries of these tectonic plates. Now, if we look in a little bit more detail, it unfortunately gets a little bit more complicated. So if you've done any kind of geology or earth science, or you've studied the earth in any way so far in your academic careers, you may know that when we look at geology, things are always more complicated than we first think. And so here is an example of this complicated behavior. If we look at where the continents are running into one another, so where we actually have a interaction between two continents at a boundary, so say India here is a well-known culprit that's running into Asia, so it's fairly rapidly on geological rates colliding with Asia. In these areas where the continents are coming together, things get a little bit more complicated than at places where we have things in contact with the oceans. And so these are continent-continent collisions, and within the continents in these areas, we see that the earthquakes are actually much more widely distributed. So all of these dots represent an earthquake that has happened in our record. There's more than this, but this is just some of them. And so we see here, like in the Himalayas, the big mountain chain here, and all over Central Asia, there's a much wider distribution of earthquakes than what we saw in that last image that we could just pick out kind of where the plate boundaries were. And that's true for the Middle East, for Turkey, for the Mediterranean and Greece, and for Italy. And so here, where there's kind of interactions, what we call the Alpine Himalayan collision belt, we see a wide area of earthquakes. And here, those stresses of the plates interacting are actually distributed over a much wider area. This is because of the nature of the material. We won't go into that. But basically what we see are lots and lots of fault lines that are covering this whole area. And here with any one of these faults, they might have an earthquake. And if we so these are actually colored based on when they have happened. So we have recent earthquakes in red, and we have earthquakes of the last century in blue, and then historical events. So places where people have actually recorded when their towns have been shaken and they've said, oh, there was an earthquake here. So lots where people were living along the Dead Sea and in various other places where humans have been living and recording this. We can see that. Now, so we have lots and lots of fault lines. We have lots of earthquakes, but there's actually probably more fault lines that we don't quite know about that may also have an earthquake in the future in these areas. So it's so complicated that not every single one of these faults has had an earthquake, and we may not know things like how often they have earthquakes because there's so many. And so our job becomes a bit more challenging in working in these areas, but also there's a lot that we can learn. So today when I'm talking through kind of some of the basics of earthquakes, most of the images you'll see are from either Mongolia, so this region here in Central Asia, or from Italy. And that's because these are places where I've personally worked a lot in my career so far. So some of the photos come from these places. And so these are examples of where we've really got this kind of large scale, very slow rates of earthquakes. So they're not happening very often, but they're a kind of challenge in that way, but they still can happen. So first of all, what is an earthquake? Some of you guys might know this already, but an earthquake is actually just a huge release of energy. And so that energy is stored in the Earth's crust as stress. And the stress builds up as a result of those interactions between plates. And so those are forces as the plates move around. You know, huge forces build up. They build up on kind of weaknesses in the crust that we call fault lines. And then that energy is released in an earthquake. And when the earthquake happens, the energy that's released comes out as seismic waves. And so the strong shaking that we feel in an actual earthquake. There's also significant amounts of heat released on the fault line itself. So if you move your hands together really fast, that friction builds up heat. And so that's basically what happens on a fault line. You build up a lot of heat as it moves. And some of the energy that's being built up by plates running into each other is released as heat. And then also we get this shift in the ground. And we can often see the movement in the ground at the surface of the Earth. And so here, this is another photo of that same fault line that we saw in the very first image in Italy. And this big stripe going across the ground here is the motion that happened in one earthquake in 2016. And so there's me and my PhD student for scale standing next to it. So the total movement of the ground was about the same height as us. And that happened in a few seconds. And that's also part of the energy, is just the shifting of the ground that's released. And over lots and lots of earthquakes, these kind of build up over time. And so if you look at a mountain range in places where we have earthquakes, often those mountains are actually built by lots and lots of earthquakes building up over time. And that can give you a sense of geological time as well. That represents a lot of earthquakes when we look at a single mountain. Okay, so these earthquakes are happening on fault lines. As you may know, you've probably heard of the San Andreas Fault. So this is an aerial image of the San Andreas Fault. You can see this clear line in the landscape. And these things some faults are very, very clear, like San Andreas. And that's because every time there is an earthquake, we have shifted the ground. So the San Andreas Fault isn't moving things up and down, it's moving things side to side. And we get things like these rivers getting offset by the fault over time. So this river used to be connected up here, but now it's moved by quite a long ways to get over lots and lots of earthquakes. So San Andreas is kind of a usual suspect. We certainly know about that fault, but there's lots of areas, like when we were looking at that big map, that are covered in many fault lines. And so in Italy, this is what the picture looks like. So here we just have a topographic map. The mountains are in white. You can see Rome here, which you're probably familiar with. And then the Apennine mountain chain next to Rome is covered in fault lines. And we know these fault lines exist because we geologists have found them in the field. But also we know that lots of places in Italy have had earthquakes in the past. And so in red here, you can see where villages have been kind of shaken over the last 600 years in this region. So there's a long record of earthquakes happening here. But despite, how many, Italy has a great record of earthquakes, but there's still lots of fault lines here that haven't had an earthquake in that time period, but they might have one in the future. And so hopefully you're starting to get a sense of what we geologists are trying to do. We're trying to find these faults. Now, when we think about an earthquake, we've talked so far about what happens at the Earth's surface, but if we look, I probably need to sorry. If I do that, yeah, sorry. If we just play this little video, we can see that if we think about an earthquake happening, actually a whole plane breaks from the surface down to great depths and moves in the earthquake. So this is something that just kind of keeps happening every time there's an earthquake. We can think of it going down deep into the earth. And it's not just a single line, but it's over a whole big surface. Let me just bring my pointer back. And if we imagine that we could look at this fault plane in a view where we're looking along the fault and at depth, so down to 30 kilometers or so down below our feet, we can imagine seeing this fault line in space. When an earthquake happens, it actually ruptures. So the word rupture means it breaks along quite a wide surface of this plane. And so often when you see earthquakes reported on the news, they're just plotted as like a point on a map. But actually it's more like a wide rectangle or oblong shape that is breaking over a large area. And so sometimes this length scale can be tens to up to hundreds of kilometers. And the size of an earthquake magnitude, so how strong it is, corresponds to this kind of patch of the fault that moves in the earthquake. So if we have a really big patch of fault that moves, and so this whole area of the earthquake kind of, you can imagine it spreading out over the fault, and it starts in one spot and it goes out and moves and releases all that energy, that the larger the patch, the bigger the magnitude. And so in a really big earthquake, like a magnitude 9 that affected Sumatra, we might expect to see hundreds of kilometers of fault moving, whereas in something like what we saw in Italy, that was a magnitude 6.6, probably about 30 to 40 kilometers of that fault moved in this length, and then also at depth, down to tens of kilometers. And so if we have a really small earthquake, then only a small part of that fault line actually moves in the earthquake. So that's one thing that we kind of know, that faults scale with the energy that they release. There's lots of neat things that we can use in our science based on some of these facts. Now, when we think about, so we've thought about what do faults look like, what do they look like at depth, what's happening on the fault. Let's think through time as well. So if we imagine we have one fault and we're thinking about geological time, so going from today back in time or even forward in time on this fault. So say we're today and we're looking back, it doesn't really matter which way time goes on this graph. But what we think of happening is that stress is building up on the fault from plates moving around. And then we think the really simple way of thinking about faults is that stress builds up to a threshold and then it fails in an earthquake. And so our stress is building up and it fails, it builds up and it fails. Now, if this was the case, our job would actually be pretty easy because we could estimate how fast the stress is building up. We might know some threshold that the fault might reach, and then we say, okay, it's due for an earthquake. So that's why you might have heard, like in California, they often say they're due for the big one because it's been a long time since the last earthquake happened on that fault. And so a lot of stress is built up, and we might expect to be kind of close to this threshold. This would be great because then, yeah, we could really use that information. So if we said, oh, well, it's been, this many years since the last time there was an earthquake, we know how fast that stress is building up. So we have this many years to go until the next one. But unfortunately, just like I said at the beginning, geology is a lot more complicated than that, and the Earth is more complicated than that. And this is really recent research. In the last 10 years or so, we're really starting to understand that it is a lot more complicated than that. And so we think on faults that the buildup of tectonic stress may not happen at a constant rate. And so faults can do all kinds of weird and wonderful things. Sometimes they don't flip an earthquake. Sometimes they move really slowly and stably, which makes it a lot more complicated. We think that the strength of the fault, so that threshold value, might actually vary over time, depending on what's kind of happening to the fault. And so it gets a lot more complicated. And actually, if we're on a fault that it's been a really, really long time since there's been an earthquake, but we're kind of at this imaginary point in time, we may not be able to say exactly, when the next one is going to be. And faults might also experience periods where they have lots of earthquakes in a short period of time. And so it might be that, well, I know this fault had an earthquake 50 years ago. I wouldn't expect it to have another one, but then it does. And so things like that make our jobs a lot more complicated. But a lot of what earthquake geology, the kind of forefront of earthquake research right now, is trying to understand this challenge and this problem. But there's also a lot of basics that we don't understand either. So there's a lot of work to do here, despite all the stuff that we do know. Despite that kind of complicating factor, there's a lot that we can still do. And this is where scientists and also geographers and physical geographers can contribute. So if we look, this is a map of hazard. And this is a lot of the things that we kind of try and talk about when we're talking about earthquakes and the effect of earthquakes on society is what is the hazard and where is the hazard? So we can see here in red, these are areas that are considered to be high hazard. So you can see Italy is a place of high hazard, Greece is a place of high hazard, and Turkey. And the earthquake that happened a couple of weeks ago in Western Turkey and in Greece was in one of these regions where it's very red, so in this area here. We're very lucky in the United Kingdom. We live away from any hazard. But if you've been on holiday to any of these places, which often we do go on holiday to some of these places, you may have been exposed to a risk of earthquakes and to this hazard. And one thing I would like to ask you guys, you can respond now or you can respond in the questions, is have you ever experienced an earthquake? So some of us in the UK might have experienced some small ones in the UK, but maybe you were on holiday somewhere and you did experience an earthquake. And so I always like to ask my audiences, have you ever experienced an earthquake yourself? They're quite scary if you have felt a big one, and the small ones just kind of feel a bit interesting and weird because you're not sure, why is the ground moving under my feet? But then when they get big, they get a bit scary. Okay, so that little interlude here, but what actually goes into making these maps? We're kind of continuously trying to improve them, actually. So the things that we use, the information that goes in, is the history of earthquakes in a region. So we might know something, we might have a very detailed historical record. We also have a record, we've been measuring earthquakes for the last just under 100 years, or around 100, over 100 years now. Yeah, and so we have like a lot of measurements of where earthquakes have happened using seismology. So that will go in, because where earthquakes have happened in the past, they'll probably happen again. We also look to actually find those fault lines, and so the locations of fault lines go in here. So this big purple stripe across Turkey is a big fault. It's one really massive fault. And so that kind of location goes in. And then also information about the rates and occurrence of earthquakes. So how often they occur and how fast that tectonic stress is building up. And so what I want to do is kind of go through a few examples of these different pieces of information that we can contribute as earth scientists to building up these maps of earthquake hazard. So the first is information on the rates and occurrence of earthquakes. One really cool technique that we have that I don't personally do, but is using satellites to measure how the ground is moving. So here in California, if you look at this map on the right, this is a map of Southern California. You wouldn't necessarily be able to tell, but what I can tell you is that this big stripe going down is the San Andreas Fault. And then you have a big basin here, and there's some other faults on the side out here. Now, and there's another fault zone over here called the Wasatch Fault. Now this map is a measurement of how the ground is actually moving slowly. So the ground moves really, really slowly around the San Andreas Fault and all of these other faults, and it's sort of building up stress. The faults themselves aren't moving until they then break in an earthquake. And so this measure, we call it strain. So that's strain that's building up, and then it's released in an earthquake. And that maps on really nicely with where earthquakes occur. So this is just a way of plotting actual earthquake locations. So someone has got all the earthquakes, like little up to big, that have happened in these areas, and they've said, well, we're in red and pink, and then yellow is where lots of earthquakes have occurred. And you can see that this map really matches on quite nicely with places in the same here in pink is where things are moving the fastest that we can see using satellites. And that really does equal out with the earthquake rate. So if we kind of step back and look at regions of the Earth that are doing what we call deforming, so they are moving, we can say, well, yeah, earthquakes are going to happen there. So that's one piece of information that goes into those hazard maps. Now, the next thing is fault line locations. And what I want to do now is kind of show you guys how to find faults. And so, as I said at the beginning, sometimes it's really obvious where faults happen. So this was a view of San Francisco after a big earthquake in 1906, and that was on the San Andreas Fault, which is our kind of usual suspect. We know where that fault is. But lots of earthquakes come as a surprise, and they keep surprising us. So this was an earthquake in 2003 in Iran that happened on a fault that was actually blind. So we didn't know that fault was there. It wasn't expressed at the surface. And the kind of local people were not aware of the risk, and so they weren't expecting this earthquake to happen. But we can do better than that. We can try and find some of these faults. So I talked about how the San Andreas is really obvious over time. Lots and lots of earthquakes move, and that movement basically gets preserved at the Earth's surface. So if San Andreas is in a desert, it's very dry here. If it was wet and forested, we wouldn't be able to see this as clearly because the effects at the surface would actually erode away. They would get removed by rain and erosion. But here we can see it really clearly. Some faults are less obvious. So the reason the San Andreas Fault is so obvious is because it has lots of earthquakes. But this is an example of a fault in Mongolia. And I'll put up some annotations in a second. But what I'd like you to do is just have a look and see if you can guess where the fault is in this picture. So hopefully you're all looking. It's very subtle. There's some mountains in the distance, and we're just standing on the side of a hill here. So hopefully you all have your guess. I'm going to reveal the answer. It goes straight through the middle of this picture. And so this very subtle change in the landscape, this little green, slightly green area next to me, that's me standing there, is actually evidence of an earthquake that's happened in the distant past. So it leaves behind a little kind of dip in the landscape because it's been offset. And then over time that kind of degrades and we end up getting something like this. So it's very subtle. And I'll show you how that kind of degradation happens. So this is a picture of an earthquake that had happened a couple of years before the photo was taken. You can see the ground is literally ripped apart. And so the earthquakes that we're talking about here move the ground side to side. They don't do vertically, but the ground has shifted and it kind of rips apart. And then this is an earthquake. It was a really big one, a magnitude 8.3, that occurred in 1905. And this photo was taken 100 years after the earthquake. And you can still see that there was something, a big rip in the ground, and it looks pretty obvious, but it's more subtle than this image here. And that's because the elements have kind of attacked that landscape a little bit and degraded the scar. And then if we look even further back, we can find little things like this. So this is just a series of kind of small ponds that formed as a result of an earthquake. And so an earthquake, it would have looked like this about 1,000 years ago, but this is what it looks like today after the elements have kind of affected the landscape. And so what we geologists can do is try and find some of these more hidden hazards and identify where they are and say, here, you might get an earthquake in the future, because we know that one happened in the past. But it's a lot more subtle than some of these like big, more recent earthquake breaks. So we have lots and lots of tools to try and figure out where these faults might be, and then also study them in more detail. So I've talked about how we can recognize those faults because they're very obvious. So here we see San Andreas in a satellite image. And what you can do is go into Google Earth yourself. If you've never used it before, it's a really fun way of kind of zooming around and looking at the Earth in different places. And you can kind of visit all these places virtually, in which now, especially now that we can't go into the field and look at them, this is a great resource. And faults have a specific kind of look about them on these Google Earth images, satellite pictures. And that's because they're really linear features. So they're this big line that strikes across the landscape, and it doesn't look very natural, but it's too big to be man-made. And so here's the North Anatolian Fault. This is in Turkey, and that was that big purple stripe that I identified across Turkey in the earlier picture. And so this fault here too makes a big line going across. I've helpfully labeled it with a yellow line, but yeah, and it's a little bit more complicated. It's not just one straight line. There's lots of other kind of smaller faults around it. But you can start to pick these out once you get your eye into it. So if we do that, let's try and get our eye into what these things look like. So here we are back looking at Mongolia. This is a satellite image on the left from NASA. And this is a photo on the ground. And so this photo is taken from down here, and it's looking off towards, this is a mountain here. This is a big lake in blue. The colors are kind of false color. So in this image, things that are wet or water or plant life turn up as bright red. And then things that are just like kind of flat, more alluvial or sandy plains are in these kind of yellows. Some of the rocks here make different colors because the rocks have different compositions, so they're reflecting the light slightly differently. But yeah, just to try and get your eye in. And all these white puffy things are clouds. So hopefully your eyes are starting to maybe pick out some lines. And so here's one up here. We can see a real change. So on this side, there's a bit of a mountain and rivers being incised. And on the other side, it's flat. And so that's actually a fault. And there are loads of these things across. So we're actually standing here, and we're looking off in this direction along a fault. And this is what it looks like in the field. So it's not very strong. You have to really kind of know what to look for. But there's a slight change in the landscape. And that's because we're sloping downhill. And then this bit of the ground is just slightly up because it's been shifted around. So if I take that away and then put it back, you can start to see some of those lines. And this is what we do. We look at Google Earth and we try and say, well, where are these faults? And can I go into the field and look at them? Here's just another example of one. So these faults that move the ground side to side, strike slip faults, have a very distinctive trend in the landscape. We call them mole tracks because it just looks like a giant mole has sort of dug under the ground and made a bunch of hills and holes as it went along the fault. And that's just because when the fault is at the surface, it sort of wiggles back and forth and it creates little areas that are being pulled apart and pushed together in each earthquake. And so over time, you build up these kind of big holes and ridges in the ground. Mongolia is another place where it's very dry. And so often you find the vegetation growing in these little tracks. And so they get a bit obvious when you start to see them. So in the past, this would have been a really big earthquake. And they look, again, very distinctive. So this image is from ESA, which is the European Satellite Agency. And we can see striking across the landscape, very obvious evidence of an earthquake rupture. And this earthquake rupture is so old that it wasn't recorded by our seismometers, but it happened at some point in the past. But we can still see it on satellite images. So that's pretty cool. And if we can map out the whole thing and go and visit in the field, we can start to estimate how big that earthquake was and how often that fault might have earthquakes as well. So we look at satellites, which is a lot of what we're doing right now because we can't get into the field, unfortunately. I'm a field geologist at heart. I love doing field work, and I haven't been able to do any this year, but that's okay. But yeah, field work is great. It's really fun. So if you're interested, if you like going outside and doing fun stuff, then you should consider a career in geography or geology because we get to go outside a lot. So sometimes field work is kind of challenging. Here we got stuck in the mud overnight and we had to get help from a nearby village for people to like drag our vehicle out of the mud, which is always an adventure, but it's also beautiful So here's another example of an earthquake rupture in Mongolia. And then here's some sampling that I did last year in Turkey, looking at a fault in Turkey that is more of one that moves things vertically. You can see we collected samples from this fault scarp here. So this is an actual fault scarp that's been exposed over time. So we get to do lots and lots of field work. And often when we're in the field, we find things that may be impossible to see from satellites. So this is a big fault in Italy that you couldn't really see in satellite imagery because it was covered up by these trees. And then here's a very subtle fault in Mongolia that was quite hard to see on the satellite imagery. But then when we got there and we could actually walk along it and get to know it a bit better, we could say, oh yeah, this is an active fault. So us earthquake scientists, we have to do field work if we want to. And yeah, that's always really good to find something that you can't really know is there until you get out into the field. And yeah, we can also even use things like, this is just another example of a satellite image. So this is of the same area, but this is a very old Landsat image that was taken in the 70s. And we can see a fault line running across this image. It's a big line. And then if we look in more recent imagery, technology is always making our job easier. And we can see that same fault in much more detail. We can see it actually goes underneath this frozen lake, which is pretty cool. So we can find all kinds of things. And that's from the kind of prehistoric record. And then finally, another tool that we use is, and I won't go into very much detail on this, but we try and actually date fault movements and use various chemistry and physics to date when earthquakes happened in the past on these big scarps. And so a lot of my own research is basically using cosmic radiation or space rays and chemistry to measure how the scarp is being exposed over the past few thousands of years. And these dating techniques tell us something about the rate and pattern of earthquakes that happen. So remember that image that I showed a while back of how things change over time on the fault. This research is giving us clues into how that works. I won't go into too much detail, but if you're interested, you can always get in touch. I can talk about it more. But what we're learning is that the fault lines are really complicated when we look at them over time. And so here we just see a map of Italy, kind of zoomed in from the earlier map that we saw. And each of these dots represents a different sample site that we have on a fault on all these different fault lines. And this is quite a long story short, but if we look back in time, so if we go from today back over time, over thousands of years, what we've done is measured the rate of movement on these faults. So the rate of slip, so how fast they've sort of come out of the ground due to earthquakes. Each of these lines is the data from one of these sites. So like here, Cap in blue is represented by this line. And on the y-axis here, we can see slip rate. So that's how fast it moves. And we see over time that fault, it wasn't doing very much. It had a pulse of activity and then it slowed down. And if we get all of this information from lots of the faults in the area, we can see they're kind of taking turns. So some of them kind of go for a while and then slow down, whereas others have pulses of activity. And so this research is really kind of ongoing new research that is looking into that problem of how often faults have earthquakes and how they kind of share the total tectonic load over lots and lots of faults. And this kind of information is going to hopefully help us understand what they're doing and then improve the way that we can forecast them. Okay, so that kind of tells us a lot of information about faults. I hope you've learned something about the kind of what faults are and what they do. And that whole part is what we consider the hazard. So it's a very specific term. The fault itself is the hazard to people. But we use another word to describe what people might experience, and that is the risk. So we should consider, well, what's the actual risk to people? And these photos show this very well. So here in Mongolia, this is an active fault, and so it shoots off across the landscape. And you can see these tents here. This is called a ger in Mongolian, and it's what people live in when they live out kind of in the middle of nowhere in Mongolia. Some people live in cities, but a lot of Mongolians live in these tents. And so this tent, you notice, is located right on an active fault. And you might think that that's quite dangerous. But actually, because they live in a tent, if there was an earthquake on this fault, they would get quite shocked, but they wouldn't be very injured, because even if the tent fell down, it's likely that a human could survive this collapsing, or they might be outside working, and so they're very unlikely to suffer major casualties from an earthquake on this fault that they're literally living on. Now, if we look to these photos on the right, which are quite upsetting, this is a building that collapsed in the city of Izmir in Turkey after the earthquake a couple of weeks ago. And here, this earthquake actually occurred about 50 to 60 kilometers away from the town of Izmir. So the earthquake was quite far away. It wasn't right under the city, but yet there was still a lot of damage. And so despite the fact that people here were living quite away from that particular hazard, that fault, they still had a much higher risk than here in Mongolia, these people that are living right on the fault. And so we have to consider, well, what is the risk to people? So if you live in an area, if you're not in a building, then you'll be fine in an earthquake. And so it's really the buildings that kill people and not the earthquakes themselves. And that's a common thing that we consider, that us earth scientists kind of consider when we're looking at these, is, well, what is the risk? And so the risk is that part of the problem where it tells you how exposed people are to having an adverse effect from an earthquake. And if we look at this over time, we can see that there is a kind of correlation between the fatalities in earthquakes and the growth of Earth's population. Maybe not as fast as population has grown, because it's obviously grown very fast over time. So here's today, and here's looking back into the past. But we do see an increase in fatalities over time from earthquakes as population has grown. And so we know that's the first thing, is just there's more people exposed to this hazard of earthquakes. Now, if we look at kind of global casualties as a proportion of the population over time, so again, going back in time and looking to today, in general, casualties have been going down. There are spikes over time, but on average, people are safer. We have better healthcare, better sanitation, decreasing poverty levels. And so if we look globally, fatalities are going down. However, earthquake casualties continue to rise over time, as we saw in that last plot. Now, the reason for this is that more people are living in urban areas and cities with buildings, and of course, that population growth effect. And so those are two basic contributing factors to the rise in fatalities due to earthquakes. And so in blue, this is just deaths from earthquakes in general. So that might include deaths from tsunamis and things like that. And the red line here is just deaths from building collapse. So building collapse has really gone up over the last few decades, despite the fact that earthquake engineering has drastically improved over time. So the problem is a lot more complicated. And one thing that we sometimes have to think about is corruption. So this was from a really interesting study of a group who tried to come up with a corruption perception index. So the higher you plot on here, the better you are in terms of corruption. So you don't have very much corruption in your society if you live in, say, New Zealand, but in places like India and Pakistan, you might expect to see a bit more corruption. And if we just sort of plot a line, so this is plotted versus the income of various countries. And so obviously high income countries do a bit better. They have lower instances of corruption than low income countries. But if we actually try and separate out some of these factors, so if you have a low income country, then your corruption is likely to be high, but you also might have issues with poverty and people not being aware of problems and things like that. And so it's quite difficult to actually distinguish what's happening down here. But if we just look at the places that are plotting here, this is where corruption is actually probably a real problem. And so they're doing worse than what we would expect. So this line says, well, if you had no corruption, if you had a decent corruption index, you'd plot on this line or above it based on how much your country's income is. But if you plot below, it's a problem. And we saw this in Italy for sure after some of the earthquakes that have happened there. There's a lot of corruption in the building construction industry. And we can see evidence of places where buildings really shouldn't have fallen down. So student dormitories that had been built quite recently before an earthquake in 2009 that did collapse in the earthquake. They should have done better. They should have been built to code. We see places where the rebar was not installed properly. So this is like a reinforcement metal that can help reinforce the building, wasn't installed well, and so that building fell. And we see places where really similar buildings next to one another, one building fell over and the other one didn't. And so that suggests that there is corruption. In some of these buildings, like newspaper was found in the building materials to make it cheaper. And so that's a real problem. And sometimes the problem isn't just corruption. So this is the town of Amatrice, which was damaged in 2016. This is an old, beautiful village made with kind of old stones. And it's really difficult to make buildings like that resistant to earthquakes. And so that's another challenge, is just what building materials do you have? And do you have these kind of historical buildings that are more difficult to make resistant to earthquakes? It's also very expensive, of course, to build buildings that are resistant to earthquakes. So that's another challenge. And just your general location. If you're sat on top of a fault and you do live in a city, then it's very difficult to deal with that hazard. And some countries do better than others. But that is definitely some of the problems that we're aware of as earth scientists. But really, to finish up, so we and our scientists are definitely concerned with the hazard. So the part that deals with the physical nature of Earth and where earthquakes are happening. So you can see this global map of earthquake hazard. We're always trying to improve these maps and improve the way that we interpret and use these maps in order to kind of prepare societies for dealing with this and advise them on how they might want to prepare and build their buildings. But what is really exciting about the kind of research that I'm doing is trying to understand these kinds of problems. So why do faults do what they do on the kind of timescales that we can observe them as earth scientists? So that and kind of new advances in understanding this problem might help us better understand why we often get surprised by some earthquakes in places, and might help us even more improve those hazard maps. And then we can really anticipate things like this. So this is a village of Castelluccio. You might have seen images of it back in 2016. And it was destroyed by a magnitude 6.6 earthquake. Luckily, not many people died in this town because there had been another earthquake further south that happened 2 months before. And so most people were actually evacuated before the then bigger earthquake destroyed this town. So I was quite lucky for them. But other people did unfortunately die in the first one that happened. And it just caused mass devastation. So it's really difficult to recover. And this city is still not recovered. Most of these buildings have been leveled, but it hasn't been rebuilt even 4 years later. So it's quite difficult to deal with these things. So yeah, I just want to thank you guys for listening very much. I hope that you have learned a little bit about earthquakes, a little bit about what we scientists can do to study them, some kind of physical geography of what faults do at the surface, and then how that affects the kind of humans living amongst these hazards. So thank you very much. And I'm happy to answer any questions at all.
Thank you, Laura. That was great. It's really nice to see as well, like you were saying, some of the opportunities you can get by studying geography, of being able to just get out into the wide world and see all of these really incredible formations, just like in this last slide you show, I guess, just right on the surface.
Yeah. I've gotten to travel to a lot of amazing places. Quite lucky.
Yeah. So, I mean, hopefully when students that might be watching this are getting towards, starting a career maybe in something geographical, you definitely be able to get outside a bit more and see it all.
Yeah. Hopefully by the time everyone is in university, you'd get to go on the lovely field trips that we're used to. Yeah, it's quite affected our students, unfortunately.
Yeah. And you asked the question earlier about who here has experienced an earthquake, and one person did say that there was a small one in the late 2000s, and they were very young, so they don't remember, but I do remember that one. That was in about 2008, and it wasn't that small. Well, if I'm thinking of the same one, it was in Lincolnshire somewhere, and it registered about 5. Yeah, magnitude of about 5, and I remember waking up with it. Anyway, we've got lots of questions coming in.
Oh, well, 95 will definitely wake you up. Yeah, that's pretty scary.
Okay, so we've got lots of questions coming in. Would you like to have a look?
Yeah, so someone is asking about what is the longevity of earthquake proofing? How many earthquakes then can they withstand typically? So a really good building can withstand lots of earthquakes, and it won't necessarily matter if they've been affected by multiple events. So in places where we do earthquake engineering really well, like in Japan or in Chile is also a very good place for earthquake engineering. A lot of their very tall buildings, the big skyscrapers, have been built properly to kind of sway in the earthquake. And so they're actually built to move. And so when an earthquake happens, they're fine. You might have some damage inside from a little bit of shaking, but things are fine. If often some of the what we call retrofitting is done, and you see this a lot in places like Italy, where they put metal bars through the building, and often the bar then has a tie on the outside. And that's when an earthquake happens, when a building does this, it's bad, basically. So if it was sort of staying coherent, it would be okay. But often when the shaking gets strong, they start kind of almost imploding outwards. And that puts everything into extension, and things are very weak when they're in extension. And so the building fails. But these ties are meant to keep the building together. And so if they have a big earthquake, often those ties will work to hold it in and to stop it from doing this sort of explosion where it just then collapses. But often that's just to keep the people alive. And so you wouldn't still want to live in that building afterwards. So it depends basically on how good your engineering is and what it's really been built for, whether it's been built to flex or whether it's been built just to stop people from being killed in their buildings. So after an earthquake happens, you have to do a lot of surveying to try and decide whether the buildings are safe or not. In my research, have I picked up obscure reading on seismometers, such as glacial calving or bomb testing? So I haven't personally done that type of research with seismometers myself, but that's certainly something that seismologists pick up. So anytime that there is kind of like nuclear activity or anytime places like North Korea are doing something a bit dodgy, a lot of my seismology friends can find it in the kind of global seismic network. And I have a friend who works for the US government who I think that's kind of his job is to do that and to analyze them because they have different signals. So things like bombs going off have a very different signal to an earthquake in the crust. And also, glaciers, I think people are using seismology to study glaciers and how they collapse and also how they're moving as well. So there's lots of signals that can be picked up from the earth that aren't necessarily just related to earthquakes. And people are quite interested in that. And also, if you are interested in things like fracking and whether fracking can set off large earthquakes, there's a huge field of study of how we can determine whether or not, how far you can go with fracking before you possibly trigger a large earthquake. So there's a lot of monitoring done around that. I'd like to ask a bit more about my research into cosmic radiation. Is there an email I can use? Yes. So you can get me at my University of Leeds email. It's on my website. It's just l.c.gregory@leeds.ac.uk. Feel free to give me an email. I'd be happy to come and talk to a class a bit more about that kind of specific research if anyone's interested. But it's really fun using space rays to try and work out what earthquakes have happened over the past 10,000 years. It's quite enjoyable. Did I miss anything?
No, I think that's it so far. But if anybody does have any other questions, feel free to pop them into the chat because we've got a little while left of the session. Got plenty of time. It's mentioning about using seismology for a lot of other things, and I've got this recollection of seeing something that popped up during the first lockdown about the fact that there was less seismic activity because humans weren't moving around so much.
Yeah, that was really cool. People started noticing that their seismic signals were a lot better because we have a problem with noise when we're trying to look at really subtle seismic signals. And so if you have people driving in their cars and kind of lots of building works happening, that can actually put some noise into our seismometers, and then we can't see the original because some of the signals we look at are very small. We can even see things like the tide changes in the earth, and you can even, and what's interesting is those tide changes sometimes affect very small earthquakes. So you get tiny earthquakes associated with the lunar tides. So finding signals like that is really hard. So I think a lot of people got some good seismic research done in lockdown because everything was very quiet.
Yeah, I bet. We also got a comment just coming from David Rowley who said they picked up a nuclear test in North Korea on their school seismometer.
Oh, wow. That's pretty cool. Yeah. Did the signal look different from any other of the other kind of normal earthquakes that you look at? Give them a second to answer.
Yeah, sometimes there's a slight delay.
Yeah, it'd be interesting if you could actually see the difference on your school seismometer from like North Korea compared to a normal signal. That's really great that you guys have a seismometer. That's really cool. This is, already giving a good example of, what you can expect being a geographer. Yeah, when I was an undergraduate, I went to the University of Florida, and this is kind of one of those big typical American universities that has a huge football team, American football team, and we'd play these games they would play every week, and our stadium would seat 90,000 people. So this is just on campus in America. Like, we take our sports seriously, I guess. But we had a seismometer on campus, and you could actually tell when our team scored because you could see the extra vibrations on the university seismometer, which was buried underground, like, hundreds of meters away or even a kilometer away from the stadium. And they could pick up the signal of when we scored because everyone would be cheering so much in the stadium. So it was pretty cool.
I think the last stadium I was in only had a capacity of about 13 or 14,000 people, but you could feel the slight movement, when everybody was jumping up and down when somebody scored, that kind of thing.
Yeah.
So I can only imagine what it's like with a big field full of American football players.
Yeah, it was pretty cool. Yeah, not quite a full earthquake though.
No, not quite. Hopefully not quite. That wouldn't be a very good reaction. No. So yeah, if there was that earthquake in the UK, it was in 2008, and it was in Lincolnshire, so it was on the east coast of the country. Where could that fault have come from? Because as you were showing on your map earlier on in the presentation, we were in a nice sort of pale blue color. There's not a lot of activity going on here.
Yeah, so in England, and in the UK, we actually have a lot of faults. They're just old faults. They're kind of not very active anymore. So you can have a fault that doesn't have earthquakes. And actually in the UK, we have great faults. There's loads of exciting ones that we can go and look at in the rocks, and we take our students to see them. But some of these might then get kind of reactivated. And so a lot of the activity that we see in the UK, it's either related to things like fracking, but those are very small earthquakes, or we think some of it might be related to old mining exploits. But also some of it could be related to the last ice age. So when the ice melts off of the continents, it kind of it's pushing down, and it actually then releases a lot of stress. And over time, so we're quite far away in time from that last glacial age. It's been at least 11,000 years. But there could still be just a small amounts of residual stress left in the crust from that. So that can kind of put some stress on those old faults and make them have small earthquakes. But so we would have expected actually probably more earthquakes in England and the UK closer to the end of that ice age, because the ice is removed, and that kind of relaxation then causes earthquakes. But we still might be getting a few small ones as a result. And also sea level change can affect it as well.
Okay, that's really interesting, because that ties in nicely actually to one of the previous lectures we've had with Geo, which was about glacial shift. And so it kind of links into something that was left off at a last session, bringing it into the next one. Yeah. Well, since we don't seem to have any more questions coming in for this afternoon, I think we should probably stop there. And it's a good time for me to mention that next week, leading from one session to another, we'll also be talking about tectonics, but from a different angle, with Serval Miller, who's going to be talking about tectonic hazards in the Caribbean and looking at the hazards, the impacts, and the risks and vulnerabilities in that part of the world, which should prove to be a really nice way to follow on from your research today.
Yeah, that sounds like a very good follow-on.
Yeah, okay. Well, thank you very much for talking to us today. I hope the audience enjoyed this talk, and we'll see you again next week.
Thank you, everyone.